Now just to remind you of what the function y equals sine of x looks like. It's got the shape of a wave. It's periodic. Now I've shown the first period here. The period is 2 pi, or 360 degrees. That's 2 times 180 degrees is 360. And then it starts to repeat again. So this exact same form is repeated. It's for another 2 pi radians. So x is in radians. It's understood when we're dealing with limits of functions, of trigonometric functions, where the angle is in radians. That's important. So we will be dealing with the derivative of this function, which will involve taking a limit, and we'll be using the result of a previous video, which stated that the limit as x tends towards 0 of sine of x over x equals 1, provided x is in radians. If x is in degrees, this is not true. Okay, if x is in degrees, we get something like 0.017, which I also covered in a previous video. So I explained geometrically in a previous video what is going on when we take the derivative of a function. I'll just briefly go through it here, but I won't do out such a detailed picture. If you look at the video for y equals x to the power of a half, you'll see a more detailed picture of what's going on. Basically, we're taking a point x, some point x anywhere, and we're trying to get the slope of a tangent to our function. And the way we get the slope of the tangent is to first of all consider the slope of a line that approximates this tangent. So we consider the slope of a secant through 2 points, through the point x and the point x plus h. We consider the slope of this line here. And the way we get the slope of the secant is to write down Newton's quotient. So the slope of the secant is f of x plus h minus f of x divided by h. So you've got to memorize this here. You have to calculate this quotient, and that'll give you the slope of the secant. So I haven't drawn this in much detail, but you'll see it in other videos. We're actually getting this triangle here. The vertical distance is f of x plus h minus f of x. That corresponds to y2 minus y1 in the slope of a line. And the horizontal distance between the 2 points and the secant is this distance here, which is h, or x2 minus x1. So it's the point slope formula, y2 minus y1 over x2 minus x1. Anyway, that's just a digression. I'll just quickly get on with calculating this. So we first of all calculate this. We get f of x plus h. Well, f of x, or y, is sine of x. So we're getting sine of x plus h. And we're subtracting f of x, which is just sine of x. And we're dividing by h. Now to get the derivative of our function, to get dy dx, or f prime of x, this is the same thing as dy dx, we have to calculate this quantity here. So this is what you've got to memorize. The limit as h tends to 0 of Newton's quotient. And that's given the notation f prime of x. Now if we just let h go to 0 in this, we're going to get sine of x plus 0 minus sine of x, or sine of x minus sine of x, which is 0. And we're going to be dividing by 0. As I've explained several times before, this thing is indeterminate. So we have to change the form of this. We can't use it in this form. We have to change to something that is determinate, that doesn't lead to 0 divided by 0. So we'll have to consider trigonometric identities. A trigonometric identity for the numerator. Now what form has the numerator got? Well, if you look at it, it's got the form sine A minus sine B. The sine of something minus the sine of something else. And you just look this up in your tables, and you replace A with x plus h and B with x. Now if you look up this identity, you'll see that the identity we need is sine A minus sine B equals 2 cos A plus B over 2 times sine of A minus B over 2, where A is x plus h and B is x. So we have 2 times cos A plus B over 2. So we have 2 times cos x plus h plus x over 2. And we have to multiply by sine of A minus B over 2. So sine of x plus h minus x over 2. So we have x plus x is 2x plus h over 2 here for the argument of the cos function. And the argument of the sine function is going to be just h over 2. Remember now, we'll be taking the limit as h tends towards 0 of this thing, because what happens then is that as h goes to 0, this point on the secant, which is also on the curve, will move along the curve to coincide with the point x on the curve. So the secant becomes the tangent. The slope of the secant becomes the slope of the tangent. That's what we're looking for. The slope of the tangent is the derivative of the function at x, the derivative of sine x at x. So what we will be doing, as I said before, is working this identity in limit as h tends to 0 of sine of h over h. Well, h or x, it doesn't matter. And you can see what's happening here. As h goes to 0, we have a sine h over 2 here. But as I explained in a previous video, as h goes to 0, h over 2 will go to 0. So we'll have to have a h over 2 here. So we can actually have h over 2 here, as long as this thing goes to 0 as h goes to 0, which it does. If h goes to 0, h over 2 will go to 0. These must be the same. And as I explained before, this is 1. If your angle is in radians, which it is, of course. So we need to put a h over 2 here, but we can't just throw in h divided by 2 without compensating. And to compensate, we'd have to multiply the denominator by 2. Okay, so we're trying to fix it up so that we can apply this limit here. Okay, so you'll see this in earlier videos. I explained this in great detail. So that's what we do. So we just stick h over 2 and then we just compensate by putting a 2 here. And let's see what we get now. This thing is going to be, well, these 2's will actually cancel. We get cos of 2x plus h over 2 multiplied by sine h over 2 times all over h over 2. So I've actually factorized this single fraction into 2 fractions. These are the 2 fractions. Cos of 2x plus h over 2 all over 1. That's just cos of 2x plus h over 2 times sine h over 2 divided by h over 2. So factorize it into 2 fractions. Of course, dividing by 1 doesn't matter. So basically, we can just shift the h over 2 in underneath the sine term. The next thing we'll be doing now is taking the limit as h tends towards 0 of this thing. And that'll give us the slope of the tangent. So I'll do that in the color of the tangent, which is green. Limit as h tends to 0 of f of x plus h minus f of x divided by h. This thing is our derivative, is f prime of x. So what happens? Well, as h goes to 0, we're going to get cos 2x plus 0 over 2, or just cos 2x over 2. But the cos of 2x over 2 is just the same thing as the cos of x. The 2's cancel. Times the limit as h tends to 0 of this thing, as I've already explained, is 1. So cos of x times 1 is cos of x. So that's the derivative. That's dy dx, or f prime of x. Here's a graph of cos of x. It's actually got the exact same shape as sine of x, but shifted. If you could imagine shifting this graph to the left by 90 degrees, or pi over 2, this maximum point here would end up here. By the way, this is 1 here. And this here is 1. The cos of naught is actually 1. Now, the derivative of sine x is cos x, as we just saw. That means if we take the slopes of tangents to this curve, we'll have this curve here. So let's just examine some of this. Let's look at the derivative of the sine function at x equals 0. So the tangent to the sine function at x equals 0 has actually got a slope of 1. It's actually a 45-degree line. The slope of this line is 1. And the cos of 0 is indeed 1. Okay, so that makes sense. Now what happens as x increases? Well, the slope and the tangent will keep on decreasing. The tangents will level off until we come to this, let's say the very top of this local maximum here, where we'll have a slope of 0. So the tangents are actually decreasing in slope. So that's exactly what's happening here. The cos function is decreasing as x increases from 0 to pi over 2, or 90 degrees. until we get to 90 degrees where the cos of 90 is 1. Or sorry, 0. The cos of 90 is 0. So the slope of the tangent at 90, I just get rid of this here and just indicate pi over 2 or 90 degrees on this diagram. Pi over 2. The slope of a tangent to y equals sine of x at pi over 2 is 0. Okay, we have a local maximum. And the cos of pi over 2 is actually 0. What's happening then, as x increases from pi over 2 to this value here is actually pi. Okay, this is meant to be midway between pi over 2 and 2, and, well, not midway actually. We've pi, then we've 3 pi over 2. Yeah, this is correct. What's happening then is we move from, as x increases from pi over 2 to pi, the slopes of the tangents become negative. See, if we take a value of x here, then the derivative is negative. The slope of that tangent is negative. And that's what's happening here. The cos function becomes negative as x increases from pi over 2 to pi. But at pi itself, we have a tangent actually with a slope of -1. And that's the minimum value of the cos function, is -1. This tangent here makes an angle of minus 45 degrees with the negative x-axis, or plus 135 with the positive x-axis. And then as x keeps on increasing to 3 pi over 2, as x increases from pi to 3 pi over 2, what happens is the slopes of the tangents approach 0. The slopes are actually increasing, okay, until we get to 0. So they're negative. All this section of the curve has negative slope, but becoming less negative until we get to 3 pi over 2, where we have a local minimum. So the slope of this line here is 0. The cos of 3 pi over 2 is 0. And so on. Then the pattern repeats.